Okay, so let's get started. Today we have Ara's second talk in the morning. So Ara.
Thank you, Subhojoy. And I wore my long pants today, my only pair. So if you didn't see it already, there's an email from Subhojoy about a picture after the lecture or during the lecture. After the lecture, yeah. Okay, so I want to continue with where we left off, and I'll recycle through some of the things that we talked about last time, in case you weren't here or need a reminder. So we remember that I had three questions about the geodesic flow. There's the geodesic flow, and there was a question about what are the closed orbits, okay? What are their periods or lengths? And then what's the last question was, what's the long-term behavior under the geodesic flow? So we're going in that direction, but we've taken a diversion because the answers for finite type are well known, and we're going, this is sort of a little bit of a course in infinite type surfaces. We talked about the topology of infinite type surfaces, the classification of orientable infinite type surfaces. And then we went into the geometry of infinite type surfaces, and we talked a little bit about that, but I want to talk a little more about the geometry of infinite type surfaces today, before we get back to the questions about the geodesic flow. Okay, these were some pictures from last time of infinite type surfaces. Sorry, the slides, I do this all the time. I screwed up with the way this had to be configured, so there's going to be some cutoff stuff, but hopefully it'll be okay. Oh, I see. So now you see. So by the way, so we saw the Loch Ness Monster, the ladder surface, the Cantor-Treat surface, the flute surface. That flute surface, not the one on the bottom, but the one above it. So flute surface is I talk about it in a generic way, like the space of ends is made up of, is a set of points that converge to one point. But you have freedom as to what's going on over here. These are cusps in this picture. These are funnels. And sometimes this is useful when you're trying to look for, I mean, one fact is that every infinite type surface contains a flute surface. Okay, so you could parlay that to answer lots of questions. Anyway, I'll continue. So this is a continuation of geometry of infinite type surfaces. So the setup we had was, you have this hyperbolic surface X. So this is a complete, geodesically complete hyperbolic surface, and I'm going to say what that means over here in a minute. It's the hyperbolic plane mod a discrete group, okay? The convex core we defined last time of the hyperbolic surface, okay? And if you have a subsurface of X, and really I'm just have one example in mind, and that's the convex core. If you have a subsurface, you say that it's geodesically complete if every geodesic on it can be extended infinitely far in that subsurface, okay? So, so you can ask, when is the convex core geodesically complete? Okay, so, well, so before I get to that here, this is trivially geodesically complete. Every geodesic can be extended infinitely far. If you look at the convex core, here's an example we talked about for a finite type surface. This convex core gets cut off over here, right? Because this is a funnel over here. So, and remember the convex core, there's a number of ways of defining it. It's the smallest closed convex set that contains all of the closed geodesics. So here's an example that's not geodesically complete. And in fact, whoops. The only way you could be geodesically complete, the convex core can be geodesically complete if it is the whole space. So it has all of the funnels and whatever other pieces had to be attached, the half planes, if it's infinite type. Okay, so That was fact one. Fact two is if X has finite type, this is just a reminder, you might have to attach funnels to the convex core to get something geodesically complete. Okay, remember that the theorem, the fact is that if you have a finite topological type, then the hyperbolic surface, the convex core of it, may be, how do you get from the convex core to the full surface? You might have to add funnels. Okay? And then the other fact is that when X has infinite type, and this takes more work, then the convex core, you might have to attach funnels and or possibly half planes to get it to be geodesically complete. Okay, and we're gonna circle around to this later because I think this is sort of an interesting phenomena that occurs even when there's one topological end, like in the case of even when you're looking at one topological end. For example, the flute surface, that special end way out on the right, that topological end, when you put a geometry on there, you may have to add many, many half planes to complete the surface, okay, to make it geodesically complete, even though you're just doing this at the one end. And I'll say more about this in a little while. There's a picture that goes along with this. Questions so far? Okay, I want to sketch a proof of something for you because I think this is an amusing proof. This is to show you that for infinite type surfaces, the geometry can be quite wild. Okay, and what do I mean by that? So let me just describe what this is saying. Suppose you start with pairs of pants and you start gluing them together. Infinitely many, countably many, infinitely many. You glue them together. You know, they match up. You glue them together, for instance, like this. Here's pants one, here's pants two. By the way, I always revert back to the flute surface, but almost everything I talk about holds for all infinite type surfaces. It's just the flute surface is easier to draw and talk about. So here's an example. I take a pair of pants and I glue another pair of pants and I keep going. Okay, so we don't know what's happening out there geometrically. Okay, but what the theorem says is that if I glue these together, there's always a choice, keeping the lengths the same, there's always a choice of twists to guarantee that this is a complete surface, even if these lengths are super exponentially fast or exponentially fast, growing exponentially fast. See, when these lengths are growing exponentially fast, in this case at least, these distances between L1, L2, L3 are shrinking very, very fast. And fast enough that if you didn't have any twist here, these would converge to a geodesic in finite time, in finite distance, possibly more than one. That geodesic it would converge to is the boundary of that half plane I was talking about that you have to attach, or number of half planes. Might be more than one simple geodesic. Okay, it's not closed, but it's simple and it's complete geodesic. So does everyone understand? So the statement is there's a choice of twists to make the thing geodesically complete. I'll let you absorb that for a moment. So for example, if you don't like, talking in generality, think about the flute surface and suppose I started with this flute surface where there was no twisting, zero twisting. So these all lined up and you get this orthogeodesic that hits this simple geodesic here in finite distance, okay? And what I want to say is you can now, without changing these lengths, you could choose twists to guarantee that this is geodesically complete. And I want to outline a proof of that. Okay, so here we go. I'm I like this proof because it has a bunch of the geometric ingredients that come up a lot when you're thinking about hyperbolic surfaces in at least the way I think about them. Whoops. Oh, the proof's on the board. Yeah, the proof is here, but I might have to use the board. That's for me, not you. I should have a different color for the things that are just for me. Okay, so here's the outline. Here's what you do. And I'm going to do this for the flute surface, but this is true for any infinite type surface. The statement of the theorem, the statement of this theorem is true for any infinite type surface, but I'm going to do it for the flute surface. It's just easier to draw the pictures. Okay, so first thing you do is, I have that first, so here's this first pair of pants. Actually, this is the first one. And then the second one, let's just assume it's glued on with zero twist. Let's call that this pair of pants P1, okay? And now you're handing me P2 with this length matches up with this length, but I don't know what's happening here. And I have to choose a twist appropriately so that I can get this eventually to be geodesically complete. So here's what we're going to do. You're going to take this L1 geodesic here, right? This geodesic right here, the closed geodesic, and choose a countable dense subset of it, okay? And order those numbers. Okay, so there's A1, A2, A3. And this argument's going to be inductive. So here's A1 on this geodesic, okay? And now, look at the orthoray based at this point. Okay, so that orthoray means you're going orthogonal to this geodesic here, based at this point. So you go and you hit this boundary, okay? You may not hit this boundary. If you just stay around here for infinite time, don't do anything. Just glue P2 on, right? That's what this says. If you stay in P1, don't do anything. Just glue P2 on. But with positive probability, you will hit this boundary. So this orthoray will hit this boundary, but not necessarily at a right angle. It'll hit at some angle, okay? But here's what you could do. Now I have to glue this next guy onto here. I'm going to choose a gluing so that this smoothly connects with another geodesic. It's not an orthoray anymore from here. It makes the angle complementary angle to this one so that when you're finished with this step, you have this picture down here. This is the new piece that was added. But you add this piece so that this guy stays inside P2. So I've just built an orthoray that starts at A1 and just stays for an infinite amount of time inside this piece Y2. Okay, you might say, well, what gives me the right? Why can I do this? Why is there one of these? And the fact is that you can think of it, there's lots of ways of thinking of this. One way to think of it is that if you lift this geodesic upstairs to the universal cover, well, let me not say upstairs, let's just stay down here. If you look at vectors that make this complementary angle here along this, based at this geodesic, right? So they all go out, they're all parallel, and they all go out, give you a geodesic ray starting here. There's going to be some of them that stay inside this part, okay? That's basically the fact that in the universal cover, you're approaching the limit point, the point of the limit set. Because to hit this boundary, you have to, if you're going to hit this boundary here, this curve, you have to go into the set of discontinuity, the geodesic ray. So you can avoid that. It's measure zero, but they exist. And so you can choose a geodesic by appropriately twisting here so that, so of this family that I talked about, all these, there's at least one. In fact, there's a limit set's worth of them, the limit set being the limit set of this guy, in which you can smoothly glue this on here, and then this geodesic just stays inside here. Okay, so I I just constructed, this is step one. I just constructed this subsurface Y2 in which if you start at an ortho ray at A1, you stay inside here, okay, in this compact part. Now guess what I'm going to do? Now we're going to go to A2. Now we're going to go to A2. So A2 is somewhere along here too. And we're going to follow an ortho ray out from A2. Again, if you stay inside this part, don't do anything, just glue P3 on. I'm cool. But with positive probability, you might hit this boundary. And if you do, repeat what I just did before. Glue this P3 on so that this geodesic smoothly connects with something, a geodesic that stays inside this compact part. So I just built an ortho ray from A2 that stays inside a compact part of this surface that I'm building, okay? So I've got step one, step two. Well, now just keep repeating. A3 is somewhere else along L1. Repeat, and eventually what you build as a surface, okay, it may not be geodesically complete a priori, but you built a surface that has the property that on this dense set of points, if you go orthogonally, that ray stays inside a compact part of the surface. As they say in New York, you ain't gonna escape. All right, anyway, so you have a dense set of points here, and how does this, I claim that this forces complete geodesic completeness, that there is no simple geodesic out here in which this would converge to, these would converge to. And why is that? So does everybody understand the construction before I move on with this proof? Okay. So suppose Y is not geodesic. So let me back up. Y is this surface we just built. And I want to claim that it's geodesically complete. So suppose it's not. Suppose Y is not geodesically complete. Well, remember earlier we said if something is not geodesically complete, like this, you'd have to attach half planes. In this case, it can't be funnels because this end is accumulated on. So it has to be half plane. At least one half plane has to be attached. So here's a picture. When you attach the half plane, or say it this way, the boundary of the half plane is a simple open geodesic, and these geodesics would have to converge to it. Okay? But if that happens, the distance from this L1 geodesic along an ortho ray, the shortest one, is finite. That's how we're assuming that it's not geodesically complete. But if it's finite, lift that picture to the universal cover, and here's what you'll see. These lifts of these geodesics form a nested sequence of geodesics that converge to this L infinity here, the lift of L infinity. And this is a finite distance, okay? But notice that being a finite distance away is sort of an open condition. If I started very close to this ortho geodesic, if I started very close to it orthogonally and I still hit this boundary in finite time. Oh, but that can't happen because there's a dense set of points here in which if you go, you never get here, you stay in a compact part. Sorry? What do you mean? Yeah. No, there's no shift. Well, oh yeah, the construction, the statement is that you can choose the twist. That means that you're choosing shifts, if you like. You can choose twists to guarantee it's geodesically complete. And this is the proof of that. Right, right. Yeah. Right, right. You can do that. Right, right. You can project these points onto here, and there's an interval's worth. The point is, there's an interval's worth of ortho rays that have to start here and hit here in a finite amount of time, right? But right, right, right. That's a contradiction because there's a dense set of points that start on L1 that never get out there. They stay. Each one stays in some compact part. Okay, so again, wild geometry. Yeah. Yeah. Yeah, that's a good question. It's not, well, okay, that's a good question. Yeah. So it depends on, okay, so what does generic mean? It's in a certain sense, it's measure zero because it's a, so let's back up because let's just look at stage one, okay, that first step, right? Because you're doing the same step all the time. So when we glue P2 onto P1, so that this glues smoothly onto this, there's, in some sense, there's a limit set's worth of these. There's a limit set's worth inside this curve here. And what do I mean by that? It's a Cantor set. And the Cantor set has one-dimensional measure zero. You know, and if you don't like that, one way to think of that is P2 is uniformized by a Fuchsian group, right? And so P2 is uniformized by a Fuchsian group. And so if so this is P2. So if I look at the Fuchsian group that quotients to this has to have funnels, but I've cut them off. What do you see? I'm lifting this curve, this is L2, up to here. Here's the lift. And then there's all these other lifts of these boundary curves, right, that look like this. And you're giving me an angle, complementary angle to theta, so pi minus theta. Look at all the orthogeodesics that make an angle pi minus theta here and start from here, right? Some of them hit the boundary. We don't want those. But some of them hit the limit set at infinity. Those guys never escape P2. Yeah, you can allow it to go back. Yeah, so I was shoving that under the rug, but you're right. You can, technically, you don't have to even worry about that. Yeah, you can allow the curve to go in here and then come back out as long as it stays in this compact part, yeah. But this is really the picture. You look at, you fix an angle and then you look at all the geodesic rays that are based here at that angle, and then they go off, and then what you see out here is you're either gonna, if any one of these geodesic rays either gets to the limit set, which means you stayed in a compact part of this, okay? Or, okay, as Tengrin said, you might double back and hit over here, which means you hit a lift of this geodesic over here. That's okay, actually, but I was shoving that under the rug. Or, what's the other possibility? You might hit this boundary. We don't want that, so you throw those out. But there's still, it's the limit set, really. So to answer your question, it's this. That's what I meant by there's a limit set's worth of choices of the twist. And that could be made precise. You take this limit set and you project it onto this curve and project it downstairs to this curve, and you'll see a Cantor set in here. It has one-dimensional measure 0, okay? And those are the choice. Any one of those can be attached. I mean, you can get this picture using any one of those. Sorry? Yeah, so there's some bound, right? There's a, yeah, so yeah, the Hausdorff dimension of that limit set it's less than 1. But yeah, I'm sure that one could say more. I just don't know right now. Okay, but anyway, the point of this theorem was to show you that you can have geodesically complete hyperbolic surfaces in which the geometry is getting very wild. The lengths of sequences of closed geodesics are getting arbitrarily large. In fact, you can, this is just a side note, I don't have anything written about this, written here. You could talk about the length spectrum of an infinite type surface, and it's not that hard to construct hyperbolic surfaces of infinite type that have a discrete length spectrum, okay? Meaning discrete means under a certain number, any number you give me, there's only finitely many closed geodesics with that length less than that. Necessarily, the geodesics have to grow very fast, but there's more going on. Even in that picture, the lengths of that sequence have to grow large, but also all the other lengths have to get large as you move out too. But that's true in a very strong way, actually, that they exist. One thing that we're not going to address in this talk about infinite type hyperbolic surfaces is that there's a huge deformation space of these. And the phenomena of what's happening with the hyperbolic structure can vary wildly. Okay, so there's no, for instance, one quasiconformal class of hyperbolic structures. But we're not going to talk about that. Okay, back to the geodesic flow. Right, back to the geodesic flow. So remember question 3, what's the long-term behavior of a tangent vector under the geodesic flow? Right, so again, here's the geodesic flow. You start on a hyperbolic surface, you have this metric, you have a vector, it's a flow on the unit tangent bundle, so you start with a vector that determines the geodesic, and flowing for time t means you go along here for time t, and you pick up that tangent vector to that geodesic, the unique geodesic that started at V, that was tangent to V. Okay, there's a measure on the unit tangent bundle called the Liouville measure, and it's very naturally of this form, area measure. So the area measure on this hyperbolic surface with angle measure. Angle is the direction that V is based at that point. Okay, so I'm denoting that by d mu. And if you have some measurable subset of the unit tangent bundle, the Liouville measure of A, is yeah, I probably changed notation. It should be, I think it's mu of A in what I have written later, which makes sense. This is d mu. Okay, the geodesic flow preserves Liouville measure. Okay, it's a measure preserving flow, and here's sort of whether you like this or not. There's a reasonably nice coordinate system in which you can write that Liouville measure down in. So here's you could, if you like, you could do this in an impressionistic way, but we're going to work with this, so maybe it's better that I really talk about this. So if you have a unit tangent vector, I'm going to do this in the hyperbolic plane, and everything just descends to the hyperbolic surface that you might be working with. But I'm going to do this in the hyperbolic plane. So if you give me a tangent vector V, right, here's V right there, I'm going to give coordinates to that tangent vector. So I'm going to give coordinates to the unit tangent bundle. So here's how you do it. You have some base point that you've fixed already. Here, I'm just calling it the origin. Okay? And given V, there's a unique geodesic, oriented geodesic, that passes through the base point of V, and V is tangent to it. So here's the geodesic. That geodesic has endpoints in the hyperbolic plane. Since it's directed in this direction, I'll call this endpoint x plus and this endpoint x minus. And V is determined by those two endpoints. Okay, so if I pick those two endpoints, then there's a geodesic's worth of vectors. And then this last guy is the signed distance to A. A is the closest point to the origin on that geodesic. Okay, so in this picture, it's maybe over here, and S is the signed distance to A. So these coordinates are in the boundary, so S1 cross S1, geodesic, so you take away the diagonal, and then S is some number in real number. So I've just put coordinates on tangent vectors in the hyperbolic plane in this fashion, right? If the vector started back here, okay, then this would be negative. The signed distance is negative. All right, so anyway, I'm not going to show you why that's true, but in these coordinates, the geodesic flow, well, look at what the geodesic flow is. The first 2 points, first 2 coordinates stay constant, right? Because you're just flowing along this geodesic. That's what the geodesic flow does. If I started with V, I flow along here. So these 2 endpoints stay constant, and then the signed distance changes by whatever I flowed by. I add T. That's pretty convenient, okay? And then in these coordinates, it's obvious that, did I write it here? Oh yeah, sorry, okay. So, so we have coordinates, and here's how the geodesic flow works. Then the next thing is to write the Liouville measure down in terms of these coordinates. This is what it turns out to be. It's dx plus dx minus ds divided by the difference of x plus minus x minus squared with a factor of 2. So I'm just taking that as a black box. So, yeah. Yes. Yeah. 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 It's measured exactly in the arc length on S1. Well, no. I mean, this x plus and x minus come from V, right? Right. It's so, yeah, right. So, oh, I see. Yeah. So you can think of it. You can think of whatever way you like to do it. You've put a measure on this on the circle. You know, yeah. If you want, yeah. It's really Lebesgue. It's. Yes. Yes. Yeah. There's this. I guess there's a specific one. Yeah. Actually, yeah. I haven't worked out the coordinates.
If you just forget the Euclidean distance factor, it would still be an
Yes. Right. Right. Yeah. That's right. Yeah. You need this to get it to be the area form. Right. So dA d theta in these coordinates looks like this, and then it's clear that the geodesic flow is invariant under this. This measure the measure is invariant under the geodesic flow. Why? Because all you're doing is changing the second coordinate, the third coordinate, and d of it is 0, right? So this is clearly invariant under the geodesic flow. And again, the picture is you translate S by T if you're flowing by T. So the geodesic flow is said to be ergodic or act ergodically on the unit tangent bundle if whenever you have an invariant subset of the unit tangent bundle, such as this for every T, then either the measure of that set, invariant set, is 0 or its complement measure is 0. Okay? So there's nothing that's sort of non-trivial that's kept invariant. By the way, the measure of the full space, the unit tangent bundle, could be infinite, and it is infinite when the surface is infinite type, for instance. A good gut check is the geodesic flow is ergodic implies that there's a dense orbit in the unit tangent bundle, right? If there wasn't a dense orbit, then there's going to be a patch in which you miss by the orbit of the geodesic flow, and then you can use that patch to construct an invariant set that has positive measure. So you always have this, and in fact, this is an equivalence when X is closed, a compact. I don't think it's an equivalence when the surface is infinite type, but I'm not sure about that. So just a side note, on the flat torus, the geodesic flow is not ergodic, right? You can't, yeah, so one way to say it is there's no dense orbit in the unit tangent bundle. There's a dense orbit on the surface, right? Any rational direction, but there isn't a dense orbit in the unit tangent bundle of the torus. Just a side note for your entertainment pleasure. So I'm gonna, you see over here, this is a note for me. Might skip this. We're skipping it. Don't read the green. Don't read the green. I realized this later. I should write things in green that I don't want you to look at, but I'm going to. Okay, so what happens again for finite type versus infinite topological type? So if X is finite type, topological type, then it's pretty simple what's happening. If X has finite area, so it could be, finite area means that the hyperbolic surface either looks like this or has cusps, but it's still finite area, no funnels, then the geodesic flow is ergodic, okay? That takes work, a lot of work. I'm not going to prove that for you, but if X, in the finite type case, if X is infinite area, then you're guaranteed the geodesic flow is not ergodic. If you're infinite area and finite type, you have to have attached funnels, and that could be parlayed into showing the geodesic flow is not ergodic. And in fact, we're going to do a little exercise right now to do this computation to show that the geodesic flow is not ergodic. Yeah, so we'll prove this. That whenever you have an infinite area finite topological type surface, then the geodesic flow is not ergodic, okay? You can imagine what to do, but I'm amused by this little exercise. So here's one. So I have to find an invariant set, right? I have to find an invariant set that has positive measure. So here's one way to do this. There's lots of ways to do this. Choose a simple orthogeodesic, oriented orthogeodesic. Where's the picture? Did I lose the picture? Oh yeah, here's the picture. So yeah, let me draw the picture. So the orthogeodesic is in red here. So X has this boundary geodesic, and then this funnel. Pick an orthogeodesic. Okay, orthogeodesic means it's a geodesic that's perpendicular to the it starts perpendicular to the boundary and finishes perpendicular to the boundary. The orthogeodesic red, yeah. Okay, so start with an orthogeodesic, right? And I'm going to construct, look at this bundle of vectors, in the unit tangent bundle. So these are tangent vectors to, certainly these are included. Any tangent vector to this geodesic along here is included. And actually even the backward orbit I'm going to include. So all the tangent vectors to this. But more than that, there's a whole family of geodesics that start perpendicular here. Did I have a color for that? No. And then maybe they can't hit perpendicular to here and still be homotopic to delta, but they'll hit at some angle. And then once they go into the funnel, they can't come out. So there's a whole family of these geodesics. And they sort of make a little band around here. That's what I've tried to illustrate over here. Whoops, back up, sorry. That's what I've tried to illustrate here. Here's delta, and then there's a whole family of ortho rays that start here and stay in the same homotopy class, rel the boundary, okay? And if you look at that, so if you look at the tangent vectors of all of those geodesics, that's what I'm calling A delta. That's a subset. That's a subset, subspace, submeasurable subset of the unit tangent bundle. Okay. And now, what's the measure? What's the measure of that A delta, right? It depends on delta. What's the measure? And that's what I want to compute now. I want to compute the measure of this, the Liouville measure. So how do you do that? Well, we have the measure upstairs in the unit tangent bundle. So lift this picture, all these vectors up to the universal cover. And what you'll see is, so back up a minute again. This was beta, so there's the lift of beta, right? And then there's another lift of beta, conjugate to that. So the picture looks like this. Here's beta tilde, and here's another lift of beta. And then the delta tilde is some orthogeodesic that goes from beta tilde to beta double tilde. And then these other ortho rays go through here and hit over here, okay? And so what's the measure of that set of tangent vectors there? Well, you just need to know those tangent vectors are on these geodesics that have endpoints in this interval and in this interval. And if you go all the way from back and forth, then in the coordinates that we talked about, the x plus, x minus coordinates, you start anywhere in I, right? And you, all those tangent vectors along there up until the endpoint being j, so that's the x minus, so x plus ranges in I, x minus ranges in j, and then s, which was the distance from the closest point to the origin, that's varying between minus infinity and infinity, right? S was the sign distance, and I'm looking at all the tangent vectors along here. So that's between minus infinity and infinity. And obviously, that's infinity, because all you need to know is that this integral in here is positive. The double integral with respect to x plus and x minus is positive, and then the integral on the outside is infinite, obviously. So the measure of A delta is infinite. But I could have done this with another delta. And that other delta provides, so pick another orthogeodesic, call it delta prime. And for ease, I'm just assuming these are simple. The orthogeodesic doesn't have to be simple, but pick another orthogeodesic, say delta prime, and do the same construction. Get A delta prime, okay? All those tangent vectors are disjoint from A delta, And the same argument, the Liouville measure of that set is infinite. So I've just provided, this measure is not zero. Its complement clearly has measure infinite. So this measure is infinite, and its complement has infinite measure also because it includes this. So not ergodic for that reason. Okay, so it's sort of like a very easy example, but just to give you a feel of computing with these coordinates. Okay, but you know, in other talks I've given on this, I never did that. I just said it's obvious, it's not ergodic. You're not going to come back. You know, what was it? Yeah, right. As they say on the street, you ain't coming back, right? You ain't escaping and you ain't coming back. Got that recorded up there? Yeah. Right. Which have positive measure. I mean, infinite measure in this, right. Is it true that the boundary of which set? Right. Okay. Well, it passes through. So let's just look at delta, right? Here's delta. It goes out to infinity in both directions. I'm including that. And then the ones that are close that go out, that are in the same homotopy class as delta, they do the same thing. They start perpendicular. Well, they start here, not perpendicular necessarily, and then go in here and then just go out there. Once you go into the funnel, you can't come back. Right. Not sure if I answered your question. All right. Okay, so what happens for infinite type? So this discussion was for finite type. That wasn't intentional, but it's pretty funny. Okay, so here's our goal for today. Find, well, okay, so we're not going to get to this, but here's a question that comes under the category of the type problem, okay? And I'll explain what type means in a moment. Find necessary and sufficient conditions using Fenchel-Nielsen parameters so that X has a geodesic flow. So find necessary and sufficient conditions on X in terms of the geometry, right? How can you use Fenchel-Nielsen parameters? Fenchel-Nielsen parameters are, in those constructions of the flute surfaces, you're picking the lengths of the curves and the twist parameters. And more generally, you have the same thing. If you had an infinite type surface of some other topological type, you pick some Pants decomposition, and then you can pick lengths and twist parameters. I'm carefully saying the word parameter, and I'm not saying coordinates, because I'm not thinking of coordinates here. That's a different story. Those are marked objects. That's a different object, and it's a different object for a discussion for another day. Today, I just mean, when I say Fenchel-Nielsen parameters, you've chosen the length of the geodesic you're looking at, and when you glue, you have, if you normalize, a number between -1/2 and 1/2 that glues on, and I'm not thinking of marking it all. Okay? You'll see in a moment. And I'm going to focus on the flute surfaces because, again, those are the easiest to talk about. So what I'm going to talk about is joint work with my Hrant Tokobyan and my co-authors and Dragomir Saric. Oh, I got the accents right. That's good. I usually forget. Yeah, this appeared in 2022. Okay, so why is this called a type problem? So now I'm going to, I talked a little bit about the complex analysis of Riemann of a hyperbolic surface, the Riemann surface structure. And there's an interplay here, and this is one of the fascinating things about the subject, is that you can try to toggle between these two structures, the complex analytic viewpoint and the hyperbolic geometric viewpoint. And the point is, it's very hard often to go back and forth. And that's why we found this question sort of, well, at the very least amusing. We're starting with something complex analytic. And why? Because, let me just explain. If you start with the Riemann surface, X, we'll say that it's parabolic type if it doesn't carry a Green's function. Okay, you don't really have to know what a Green's function is, but let me just say it anyway. It's a harmonic function on the surface that has a logarithmic singularity at a point. Okay? You don't really need to know what that means, but that's what parabolic type means. Now, I was going to say spoiler alert, but let me say Athanase alert, because Athanase is not going to be happy with this language. He once told me he didn't like this language, but it's not my choice. This was Alfor's. The reason why he didn't like this language was because you think of parabolic as Euclidean geometry, and you know, this has its origins in the proof of the uniformization theorem, Kerber uniformization theorem. But at some point, the classical complex analysts started investigating Riemann surfaces, not just simply connected ones, that had or had not carried Green's functions. So they gave the name parabolic type. And it was a couple of years ago when I think Athanase was not happy with this language. But I blame Alfors. I don't know, someone could answer that, maybe Shigo-san. I'm not sure, he's right next to you. I don't know. It's true that the harmonic measure at infinity is 0, if that helps. That's equivalent to not having a Green's function. In fact, here's a bunch of equivalent conditions for being parabolic type. And this, you start to see the marriage of, there it is. You start to see the marriage, these are all equivalent 1 to 5. You start to see the marriage of the hyperbolic geometry and the complex analysis. And so X's parabolic type is equivalent to harmonic measure at infinity is 0. Okay, maybe I'll say what that is in a moment. That's equivalent to a family of curves from a compact part of X that leave every compact set having infinite extremal length. That we're actually going to talk about in this in today's arguments. And that's equivalent to the geodesic flow being ergodic on your hyperbolic surface. That's equivalent to the Poincare series at the exponent 1 diverging. This is called divergence type. And that's equivalent to the Fuchsian group gamma acting ergodically on the product of the boundary. So these are, you could think of this as the last 3 are involving the hyperbolic geometry, and the first 3 are involving the complex analysis. Yeah?
What is the measure on the boundary?
Yeah, so
Part 6?
Part 6. It's Lebesgue measure. So the first 3 are complex analytic, the second 3 are hyperbolic geometric. This is what we're going to use today. The relationship between extremal length for a family of curves and the geodesic flow being ergodic. This is where our work started, which we realized this is a very handy tool to go from extremal. So once you know these are equivalent, then you could work with extremal length and try to get the relationship between extremal length and hyperbolic length, which is doable, at least in some simple setups like annular regions. Yeah, sorry, yeah. So X is, I didn't write it, yeah. X is an infinite type surface, and it's of the form hyperbolic plane mod a Fuchsian group. And there's a lot of names associated. This is not trivial, these equivalences. There's a lot of names associated to this. Here's just a couple of them. I didn't write everything down. And there's a lot of equivalences here. There's statements about equivalent statement using Brownian motion, and lots of other equivalent statements. I'm just writing down a few right here. But the important thing is, if you like, just take this as a black box. The geodesic flow being ergodic is equivalent to this statement. And I'm going to explain what this statement is. Yeah, I think so. I think it, yeah, unless I'm missing something, yeah. Okay. So back to the flute surface. So I'm going to take a flute surface that has cusps out here. By the way, sometimes this, often we call this a tight flute. Like a tight pair of pants, it's tight flute because these are cusps. So here was our construction of one, right? And these parameters, these are geometric parameters. The LNs are the lengths of these curves, right? And the TNs are the gluing parameters. And the TNs are between, we think of them as between -1/2 and 1/2. If it was 1/2, then you're gluing, so if this twist parameter was 1/2, this cusp would point down, and so on. Okay, so these are coordinates that are assigned to this flute surface. They uniquely determine the flute surface up to isometry. Okay, so here's a cool fact. So this is geometric, but let's look at this object as a complex analytic object. It's a Riemann surface with a whole bunch of punctures that are accumulating to something, right? I don't know what it's accumulating to, but it's a whole bunch of punctures. So if I fill in the punctures, what am I left with? I'm left with something that's simply connected. A Riemann surface that's simply connected. So if you fill in the punctures, and there's only one way to do that, you get a Riemann surface that's simply connected. But a Riemann surface that's simply connected is conformally equivalent to either the unit disk or the complex plane, if it's not compact. So, and then these points that I filled in, take them out again over here. And what you see is that conformally, this Riemann surface that I just constructed is either the unit disk minus a discrete set of points that are accumulating to the boundary, or in the unit disk, or in the complex plane sequence, a discrete sequence of points that are going off to infinity. If this happens, if the conformal uniformization is here, then the geodesic flow is not ergodic. And the reason for that is that this carries a Green's function. The geodesic flow is ergodic. The reason for that is that you can't construct the Green's function here. You know, if you try, so there's a little bit of work to do this. If you try to construct the Green's function on the complement of these points, the Green's function necessarily has to go, can be continued to these points. And if you continue it, then you have a Green's function on the complex plane, but that's well known not to exist. So this is the dichotomy that we found very interesting. Again, it's conformal uniformization. It's a conformal map. But, and we all liked the plane, so we were fascinated with this. Okay, back to here. So we have these parameters, Ln and Tn, that uniquely define this hyperbolic structure. And Tn, again, is the relative twist parameter. So it's at gamma n. And it's a number between -1/2 and 1/2. you can measure it by doing this. These are pairs of pants. There's an orthogeodesic on this side, and there's an orthogeodesic on this side. If you align the orthogeodesics, then the twist is 0. And then you can measure how far along by how far off the two orthogeodesics are between the two pairs of pants. Okay, there's some choice of orientations and things you have to do this. So these coordinates, given these coordinates, here's the theorem. Remember, we wanted some geometric conditions on sort of Fenchel-Nielsen parameters to guarantee ergodicity. So the theorem is that if you sum up these ln's and with this coefficient, 1 minus the twist parameter, and that diverges, then you have ergodicity of the geodesic flow. So the way to think of this is that these ln's, okay, it depends on the twists, but one way to think of this is the ln's, if the ln's, they can be growing, because this was already one thing that was surprising to us. You could have the lengths growing and still get ergodicity. It's just that they have to grow slowly, sort of logarithmically. A corollary of this is if you just had a half twist surface, so if the TNs are all 1/2, then this is even stronger statement that you could make. If this series diverges, then you have ergodic geodesic flow. And if you just don't care about the twists at all, the worst case is when the twist is set equal to 0. So if this series diverges, you're guaranteed ergodicity. Okay, so again, to appreciate this, I want you to, I don't know, in order to appreciate this, the thing to do is to think about ergodicity is not something easy to nail down for an infinite type surface. And at least in this small set of examples, by the way, we're doing this with the flute surface, but there's a theorem like this for all infinite type surfaces. I'm just doing it for the flute surface to make it easier. But our point is that the Fenchel-Nielsen coordinates are constructive. I mean, the parameters, this is a construction. So you can hands-on see the geodesic flow is ergodic from these numbers. Yeah. Yeah, so it has to be. So if the geodesic flow is ergodic, then the surface has to be geodesically complete. Right, because if it wasn't geodesically complete, you either have to attach half planes or funnels. In either case, you're not going to get ergodicity. There's escape routes out to infinity. Very slow. In this. Yeah, because they're sort of growing. The fastest they grow, there's some coefficient in front of the log, but they're growing like log n, constant times log n. Right. If they grow very fast, there's not much we can say. I mean, this is a difficult problem. I mean, it's not, the type problem. So that word type problem comes from the classical literature. When you go back to Alfors-Sario, and the question was, characterize those Riemann surfaces that are parabolic type, meaning the ones that don't have the Green's function, OG in the literature. So find necessary and sufficient conditions. That's hard. And so we're giving at least sufficient conditions for this. Okay, so questions about the statements? I'm going to give you the ideas of the proof. I'll give you the ingredients of the proof. Yeah, so they're not. Yeah, the question was, how necessary are these conditions? They're not. There's examples where you can, that's the problem. In other words, there's not enough information, I think, in the in the conditions there to guarantee some sort of equivalence with ergodicity. Right. Yeah, that's a good question. we don't know. We don't know. It's geodesically complete. You'd like it to be ergodic. I don't know. But there are examples of infinite type surfaces where the links are growing fast and the geodesic flow is still ergodic. So that's, yeah. So let's just focus on, suppose we had zero twist in this construction. So the TNs are all zero. Then you get a complete characterization of what's going on. This is a corollary of this. So if the flute surface has zero, zero twists, then all these are equivalent. So in this case, we can have a necessary condition. The geodesic flow is ergodic is equivalent to this series diverging, okay? And that's equivalent to geodesic completeness. But that's, that's a strong assumption. The twists are all zero. And in fact, you can say more about what the shape of this space X looks like. If X had zero twists, right? Remember that conformal embedding, conformal map to the plane. So if it has zero twists, there's a symmetry here, right? There's front-back symmetry. So there's a line of reflection here. And what that means is that these punctures have to be lined up on a line, either in the unit disk or the complex plane, depending on whether this series converged or diverged. Okay. By the way, I want to make sure we understand, this series, you're only summing over those lengths. This has nothing or very little to do with the Poincare series associated to the surface. Because then the statement would be trivial. Poincare series is divergent if and only if geodesic flow is ergodic. Here, we're nailing down some special class of geodesics to get this result, or the earlier this result. So you could describe completely, that's the point, of zero twist. And you can say more in the symmetry case. You can, if there were, so by the way, so now this gives me an opportunity to point out a little bit about this stuff about adding half planes to complete the surface. So this surface, the hyperbolic geometry on this surface where the series diverges has to be geodesically complete. Ergodicity implies geodesic completeness. So the geometry on this, if the series diverges, is geodesically complete. And that means that you're not attaching any half planes. Okay? If you're going to be geodesically complete, you're not attaching any half planes, and certainly no funnels because there's no boundary geodesics. But if the series converges, okay, then this guy looks like this. And conformally, what you're doing is, and here's the picture associated to this, in the zero twist case, what you have is, remember in the zero twist, in this case, these geodesics, since this series is converging, these geodesics pile up, and you have something that's not complete. And there's a simple geodesic out here that they're converging to, maybe more than one, but in fact, it's only one. And you could see it in this picture. Here's those geodesics here, the L1, L2, you could think of them as these. Right? These are each pairs of pants with one cusp. And what's happening is that these are growing ever larger, and they're converging to this simple geodesic here. This is not a closed geodesic because it's off at infinity here. It's simple. And the half plane that you attach, whoops, is right here. I mean, this is not a hyperbolic picture, but I think it makes a good point. Whoa. So in this case, with zero twist, you have to attach, if the series converges, you have to attach one half plane. And the picture looks like this. Okay. If, one more point, really run out of time? Thought I had another. I told you it was going to go exponentially faster. Do I have 5 minutes? That thing says I don't. Okay. Let me just say, I'm going to abandon the rest of the notes for a moment. If instead of if instead of zero twist, we had half twist, so you half twist at every stage, so then you have a cusp pointing up, cusp pointing down, cusp pointing up, and so on. Then what happens is if the series converges, what you'll see in the conformal picture is those punctures have to line up and they converge to 2 points on the boundary. This still has one end at infinity. And the pants are sort of like this. And they're accumulating to two simple geodesics, one over here and one over here. And in this case, you have to attach two half planes. Here's one half plane, and here's another half plane. And the reason why I know these points are lined up here is because with the half twist, there's again a symmetry. And that conformal symmetry under the conformal uniformization becomes a conformal symmetry here. Well, a conformal symmetry here, we know what they are. They're conformal maps of the unit disk. And if it's a reflection, then it has to be a reflection on here. So and it has to go through the punctures. There's only one kind of reflection on here that passes through the punctures. That's why I know these line up. You could keep generalizing this, but and get more and more half planes attached. So this is just to give you an idea that even though you have one end, you might have to attach more half planes than just one. Okay, okay, maybe I'm going to stop, but let me just say the techniques involve extremal length, which is a conformal invariant. And then our theorem, we look at extremal length and we look at a family of curves that start at some compact part and go out. And remember that earlier result, it's the Alfrosario result, that your surface is parabolic type if and only if the extremal length of the curve families that go out go to infinity. And so what we do is we prove that these curve families have extremal length that get larger and larger as you move out. And we do that by using collars. And it's not good enough to use a standard collar. We have to create a slightly modified version of the collar lemma designed for our setting, because we know there's cusps here. And so when we do that, what happens is that we get a relationship between the extremal length of that collar. Where is it? So Maskett had proven that whenever you have a collar, a collar about a geodesic of length L, a lower bound on the extremal length is this, okay? Where L is the length of the collar, C is some constant. And this is a very good estimate when L is small. When L is close to 0, this is the right asymptotic. But when L is large, this is not the right asymptotic. The right asymptotic is really this. Basically, e to the minus L over 2. I've gotten rid of the denominator L. Okay? This goes to 0 slower than the other did. And we have to use this, and that gives us, so we compute this using some computations involving extremal length, and that finishes today's discussion.
Question?
What was the, could you repeat what the curve was? So which was the
Yeah. So it's a family of curves for the extremal length. And so in general, what, a standard thing to do is if you have some curve, and you have a collar around it, you look at the set of curves that go from this side to this side, and you compute the extremal length of that family.
So that's for the collar, not
Right. So
not the
yeah.
geodesics of the pants and the other stuff.
Right. So here's the picture associated to. So we want the extremal length of this family of curves that go from here to, say, the nth one. Okay. But that's bigger than the sum of the extremal lengths of these curves in here in each one of these collars. So if you could prove that the sum of the lengths of these extremal lengths diverges, then you've proven that this diverges, and you've got parabolic type, and hence geodesic flow. So that's what we do. We look at collars, but not a standard collar. We have to take a bigger one that gives you a better estimate. And the bigger one is one where it looks like this. Where is it? Oops. Yeah. So here's the curve, and it has some standard collar around it. Standard collar means you're guaranteed that amount of collar. But here, since we know these are cusps, what we do is we cut here and glue together. And now what happens is, if you have the standard collar, the twist doesn't matter. The extremal length of the curve family from one side to the other is the same, no matter what twist you pick. But the point of using this collar, which is designed for this setting with cusps, picture looks like this. If you compute the extremal length from here to here, you do get something that depends on the twist parameter, and that's bigger.
So this collar is not the set of points for which the distance to the geodesic is distance.
Right. It's not.
Bigger than
Right.
that.
It's bigger than that when the length is large of alpha, and that's what we were looking for. Yeah. So because this is going off over here. Look at this picture. This boundary of this is this annulus that has this special point, which is the puncture here and the puncture here. And we're working with this. Right. So this could be very different. One side, the distance here and the distance here, depending on the geometry of this and this. Yeah, so the question is, in the conformal picture, does the sequence have to run off to the boundary? Yes, the answer is yes, because if it didn't, you wouldn't have the right topological type. Where is it? Yeah, so if these converged inside, then you just don't have the right topological type. They have to go off to the boundary.
So do you have so your results is only for the fluid surface, right?
These examples are for fluid surface.
No, but the result about the ergodicity.
Yeah, well, okay, so there's other statements for any infinite type surface, for any infinite topological type surface, there is a statement like that.
Okay.
Yeah.
So,
yeah.
okay. What are the LNs in that case?
Say again?
What are LNs?
What are the LNs? Okay, yeah.
Yeah.
So for instance, the Cantor tree surface. right? So we're thinking of it as constructed out of, you have finite steps and it grows, right? And the number of pairs of pants you're gluing on are 2 to the n at the nth stage, right? And you're picking the lengths at each the nth state. Those are the ln's. So it's more than one length. It's n, 2 to the n, well, yeah, if there's 2 to the n, if you're at stage n, there's 2 to the n of them. And then there's a condition on how those grow to guarantee ergodicity. In that case, it actually turns out that you want the lengths to go to 0 very, very fast. And then this construction of these collars doesn't do anything for you. You have to use the standard collar.
Okay, so you have a version for every infinite type surface.
Yeah. By the way, for the Loch Ness Monster, for instance, the theorem is the same. Because for the Loch Ness Monster, you really just have that, you're gluing one, it's a torus with 2 holes, and you're gluing them on to get the Loch Ness Monster, at least in the way we talk about the coordinates. And then the theorem is the same. Those lengths have to satisfy that series condition. It's when see, the thing is, it's all about, so the topology here interacts with the geometry. If there's a lot of escape routes, right, from the topology, then the lengths have to get small fast or can't grow fast or something, right? The flute surface or anything that has sort of like one end, the Loch Ness Monster, those are all behave the same way because the topology is linear in those cases. But the other extreme is the Cantor tree surface, where the topology is expanding very fast. And that forces the geometry to, you have to have the geometry, those curves that are going out, get very short, very fast. Otherwise, there's no hope of ergodicity. But I didn't talk about it.
Any other questions?
Didn't remember how many years ago?
I know.
Yeah, okay.
But Alfor's definition is a surface is parabolic if its universal cover is conformally the plane, and it's hyperbolic if its universal cover is conformally the disk. And this is what I always told you. Now you're quoting Alfor's. For the other definition, Alford never used
okay, so you may be right in some of his papers, but in the book, Alfor Sario, he states parabolic type in this other one.
I cannot believe this. I don't know. I mean, Alford was during all his life, he was concerned with this type problem to see whether a surface is parabolic or hyperbolic.
Yeah.
And this is the definition I told you.
Right.
And I still don't know if this definition is equivalent to your definition with the Poincaré series. Alfor's never thought of it.
No, right. That's not Alfor's, right? That's more recent. That's Sullivan.
Gave a definition with Poincaré. Yeah, right.
No, right. Yes, that's Sullivan. Right.
So we still have to decide this.
Yeah. Oh, okay. So, okay. Well, but there were I listed 6 equivalent conditions, right? And the first 3 were complex analytic, and then the last 3 were geometric. The geometric equivalent conditions to the other, those are, you could call it modern history, right? That's Patterson-Sullivan, and right. So not having a Green's function is equivalent to, that's Sullivan. Not having Green's function is equivalent to the Poincaré series divergence. Oh, no, but that's a red herring. That's not, yeah.
I think like a genus 2 surface with a puncture is parabolic in this.
Yeah.
Before we thank Ara again for this nice mini course, I'd like to remind you there's a group photo after this, so please look out for the cameraman outside. So let's thank Ara.